Welcome back, everyone. I hope that by playing around with the applet, you were able to come up with answers for these questions. Let's see if we can come up with ones that we all agree on here. So A of 2 means that I'm taking the area from 0 to 2. So I've already got 2 units of area from this triangle. We're going to get another 2 units of area from this triangle because it's exactly the same shape as the previous triangle. So A of 2 will be 4. 2 plus 2 gives us 4. A of 3, we've already got the 2 units here and the 2 units here. How many more units are we going to get here? Another 2 units. So A of 3, I hope you figured out, was 6. And now we have to start thinking about signed area, as we talked about with our graph of sine of x in the previous segment. We now fall below the x-axis, and so this is, we're losing area is one way to think about it. So I've got this same shaped triangle. It's still 4 units tall and 1 unit across. So it's got an area of 2, but because it's below the x-axis, that means we're taking away the area. So we went from a total of 6 units of area. We had plus 2, plus 2, plus 2, and now we lost 2 units. And so A of 4 is 4. Let's move on to this. Where is A increasing? I hope you saw that A is increasing on the interval from where? 0 to 3. As usual, we're not going to care about whether to include endpoints or not. That's not a topic worth talking about, worth worrying about at any rate. We're gaining area whenever this graph is above the x-axis, right? We're putting in positive area, positive area, positive area all the way from 0 to 3. And then we start to lose area from 3 to 4. So A will be decreasing on the interval from 3 to 4. I find it easier to sketch the graph here and then come back and do these. So let's try that. So let's see. We know that A of 0 is 0 and A of 1 is 2. So I've got to start here and go from there to 1, 2. The question is, how do we go from 0, 0 to 1, 2 on the graph of A? Linear, concave up, or concave down? So one way to look at this is that we're accumulating area. Are we accumulating the area rapidly or slowly early in the interval? If we take a very small little delta t early on in the interval and look at how much area you would accumulate there, compared to a same size delta t later in the interval and look at how much area you accumulated there. Are you accumulating the area more and more rapidly or less and less rapidly as you go along? I hope you see that we're accumulating it less and less rapidly. Another way to think about this is, suppose this were a rate of change. F of t is the rate at which water is coming into a tank. So water starts off coming in at 4 gallons, 4 liters per hour, and then is only coming in at 3 liters per hour, and 2 liters per hour, and 1 liter per hour, and 0 liters per hour. So the rate at which the water is coming in is decreasing, and so the graph should be concave down. So I'm coming from here to here in a concave down fashion. What about from 1 to 2? I know I've got to end up at 2, 4. So we need to come up to this point, 2, 4 over here. How are we going to get there? Linear, concave up, or concave down? Thinking about it the same way, we are accumulating area slowly at the start and rapidly at the end. And so what should a graph look like? If you're accumulating more and more rapidly as you go along, that graph should be concave up. We need to get to 3, 6. But this graph from 2 to 3 is exactly the same as from 0 to 1. So we're accumulating area slowly at the start. Sorry, we're accumulating area rapidly at the start, slowly at the end. So that's another concave down one. And then we start to lose area, or we start to contribute negative signed area. And so here, let's think about this. Are we losing area slowly at the start or rapidly at the start? And are we losing area slowly or rapidly at the end? We are losing area, or losing water, or losing population, or whatever you want to think about, if it's a practical context. Losing slowly at the start, rapidly at the end. So what does it look like if you are losing more and more rapidly as you go? That's concave down. So this graph here should be concave down till the end. So that lets us answer our questions about concave down. Concave down from 0 to 1, and then again from 2 to 4. So 0 to 1 and 2 to 4. Or that was concave up, just kidding. So let's erase that. Live TV, filmed not even before a studio audience here. Concave up from 1 to 2. Concave down from 0 to 1. And from 2 to 4 at the end. You know, we want to make sure you're paying attention there at home. I hope that as I started to write that, you were all screaming. That's not the right answer. Now, let's see if we can come up with any relation between A and F. Ultimately, what we're trying to do is find an easier way to find areas under curves here. So what do you notice? A was increasing when F was what? 0 to 3. That's when F was positive. A was decreasing from 3 to 4. What was true about F there? That's when F was negative. Is this starting to sound familiar? That one function is increasing where another is positive, and one function is decreasing where another is negative. Have you ever seen something like that before? How about the next one? A is concave up when F was what? A was concave up from 1 to 2. What was true about F from 1 to 2? That was the only place where F was doing what? That's the only place where F was increasing. And A was concave down from 0 to 1 and 2 to 4. Well, what was F doing from 0 to 1 and 2 to 4? That's exactly where F was decreasing. So that should also look familiar, that one function is concave up when another is increasing, one function is concave down when another is decreasing. So at this moment, you should be asking yourself, I hope you're thinking that one of these is actually the derivative of the other. I thought we were done with differential calculus. It seems that the derivative of A is F. Just for this example, right? I mean, no proof or anything like that. But everything that we've written here does not in any way contradict this, and in fact supports it. If the derivative of A were F, then all of these things would be true based on things we already know about derivatives from our helpful chart from earlier. Now, of course, maybe I just cooked up this one function to make that happen. So let's try another function. Here, let's try one where we actually have a formula. So again, I'm going to have a function f of t. I'm going to call, in this case, it's 2t plus 3. And I'm going to create an area function, the area from 0 to x under this function f. And we'd like to find a formula for a of x. So here we are on the t-axis. We're going over to some unknown point x, and we're looking at the area under this graph from 0 to x. So what sort of shape is that? That's one that we saw earlier. That's a trapezoid. And at the time, we didn't remember the formula for the area of a trapezoid. Suppose we still don't. We can break it up into this area and this area. So what's this area? This is a rectangle. Its height is 3. Its width is x. So its area is 3 times x. This is a triangle. So its area is 1/2. The base is x still. And what's the height of this triangle? If I plug x into this formula, f of t, to figure out the y value up there, what do I get? If I plug an x in here, f of x is 2x plus 3. So that y value is 2x plus 3. So what's the height of this triangle? It went from 3 to 2x plus 3, so that's a height of 2x. Another way to think about it is just as we did with that other example, with our other trapezoid. The slope of this line is 2. Every time I go over 1, we go up 2. So if we go over x, we should go up 2x. What does this all simplify to? X squared. So what does that mean? So a of x is, I take the area of the triangle, x squared, plus 3x. Does this support or contradict our conjecture from before that the derivative of a is f? So let's check. And a prime Well, what is that? That's 2x plus 3, which is the same as saying f of x. The variable changed from t to x, right? But that doesn't make any difference. The function 2x plus 3, the function 2t plus 3 are really the same function. This is just a dummy variable. So again, it seems that the derivative of this area function is f. So the question is that true in general? And that's what we will try to determine. Well, we hope it's true in general, and we'll try to prove that in the next video. In the meantime, we have an applet for you to explore this function, and you can put in your own functions as well to see how, when you change this function f, how the area function also changes, and to see if that supports this claim that we're making here.